Hi everybody, welcome to another video on Calculus 2. This time we study more about power series. First, most fundamental power series is in the form of geometric series. Recall that for geometric series, if we have A here, then we have 8 over 1 minus R. So there's nothing new here. We just don't have the A there. So the sum of all the power is given in this form, and that is of course if R absolute values of R less than 1, meaning R is between -1 and 1. And that is R, not X. Now if we replace R by X, then we have the series of all the powers of X from 0 to infinity is given by this, and because this is where X is between -1 and 1. So it's important when we have the power series equal to something, usually it accompanied by some condition for it. Sometimes it can work for every X, or one value for X, or the interval of X. But in this case, usually when we say the power series is convergent, meaning that it has a sum and for some certain interval, and we call that the interval of convergence. So the series is convergent for some certain values of X, and that's what we study in this section and a few more. Right, definition. A power series in this form where A is the center constant, C sub k constant, and X is a variable, and the coefficient, yeah, pretty much that's what we have. The set of values of X for which the series converges is the interval of convergence. The radius of convergence of the power series denoted R. So the radius of convergence is R, is the distance from the center of the series to the boundary. So we have the interval convergence. There will be a point in the middle, a center. And then on each side, there will be a radius of convergence R. And so this point here is A plus R, and this is A minus R. The interval is from A minus R to A plus R. Now this is not very clear that should we include in a point or not, and we have to check case by case for that. But there will be a center, and there will be the radius. The radius can be the whole thing. In the next case, there will be 3 scenarios for the radius of convergence. Right. Power series. In that power series, same condition as before. So there will be 3 cases for the radius of convergence. Case number 1, the radius of convergence is equal to absolute values, meaning that the interval convergence all real numbers. Now, next we have the radius of convergence is some positive number, a real number. In that case, we have, for that radius of convergence, in that case we have this interval. And when we have R equal to 0, if the radius is equal to 0, then the series only converge at A, meaning that we only have one point for the interval convergence. Sorry, I underlined the wrong one. It should be this one. for convergence, and it diverges for that one, right? So when we write like this, this is the same thing as we say for that part, we say x is between a plus r and a minus r. Now the only problem is, like I said before, we can have equal on either one of them. We just have to check on both of them. Right, so radius of convergence, 3 scenarios, all real numbers, radius will be equal to infinity, equal to 0. The interval convergence is just an isolated point, or we have anything between 0 and infinity. In that case, we do have an interval, and we do need to check for the boundary. Right, so now we have quite a few examples here. Find the radius of convergence for each power series. Actually, I think it's even better. We should find the interval of convergence. So the radius is just a number, but the interval convergence is a lot more details. We will see it in a minute. But first, please change that to interval of convergence for each power series. Right, check the power series. Like that. So what do we do here? So of course, just going to check and see where that series is convergent, where it is divergent. So the way to do this is, for all of this, when we find the interval convergence, we will use all the radius convergent. We use the power series. Use the ratio test. That's what I meant. So ratio test. When we use the ratio test, right, for ratio test we need to know what is the h of k. So for that series, let the term be x to the k power k factorial. Right. The ratio test is we will take the ratio of the next term over this term. Don't forget there's absolute values as well. And let that be R. Right. So I have the limit as k goes to infinity. We're going to put k plus 1 in here and here. So x to the k plus 1, k plus 1 factorial. So that is h of k plus 1. H of k is the same thing. So the difference of this one with the series we tested before is this one we have x, the other series we don't. We just have k, or whatever the index is. Right, multiply reciprocal. So I have x of k plus 1 over k plus 1 factorial. Multiply reciprocal k factorial on the top, x to the k at the bottom. Now, on this one we have to keep the absolute values because x could be negative, and we need to keep the absolute values because absolute values negative is turned to positive. So if we still have x, we should still keep the absolute values. If it is only k go from 0 to infinity, we can remove the absolute values if all of them are positive. Right, so x of k plus x to the k plus 1 power. We can write x to the k x to the first power, and k plus 1 factorial. We talk about this in the ratio test. It is k plus 1 times k factorial. Then we still have k factorial, x to the k. Right. Cancel x to the k and k factorial. We have x over k plus 1. Now since k plus 1 is positive, we only need to have the absolute values at the top. Like this. Right. So that is R. Now the ratio test say that if R is less than 1, then the series is convergent. The series converges if R less than 1. Now, if this is the series, what happened? Is this less than 1? Notice that when k go to infinity, k plus 1 go to infinity. So, unless we have infinity over infinity, in which case we don't know. As long as absolute value of x is a finite number divided by infinity, it is equal to 0. So this one is equal to 0 if x is finite, and this one equal to indeterminate if x equal to infinity. Right. So for that one, we have two scenarios here. Number one, it will be equal to 0 over infinity, because that is finite over infinity. Which is equal to 0. That is if x is finite, right? Or absolute value of x is finite, either way. Or if we have infinity over infinity, in which case indeterminate. If absolute value of x equal to infinity, or we say approaching to infinity. But there's no limit, so it has to be equal to infinity. So, and of course we're not going to have this. If it is infinity over something, then that will be equal to infinity in this case. Yeah, because there's no limit for x, so that's actually just equal to infinity. So we have infinity over a constant and then just over infinity. But bottom line is, it doesn't matter. So that equal to 0 if x, absolute value of x is equal to finite, meaning that absolute of x less than infinity. Because less than infinity is finite. So that ratio equal to 0 if x, absolute value of x is less than infinity. So let me write it out. So the series converges if absolute of x less than infinity. So in this case, r is equal to infinity. So the radius of convergence. Is radius of convergence is r equal to infinity. So whatever x, absolute value of x less than is we let equal to infinity. So in this case, infinity. And the interval of convergence so if absolute value of x less than infinity, we can write that as negative infinity to infinity. So radius of convergence, when we write in that form, absolute value of x and something less than, that will be radius of convergence. And interval of convergence is between negative infinity to infinity. Yeah. If we want to write out, it will be like this. Have a number line. And when we write this, actually x minus 0 less than infinity. So 0 is the center. And the radius of convergence could be as far as infinity. So that is interval convergence. Right. When we have a particular number, it will make a little more sense than this. But that's the first example. Right. Next, let's find the interval convergence of this problem. So we do the same thing, the ratio test. This one will be a little more work than the previous one. Right, so let a sub k be that term. Right, the ratio test R equal to limit at k go to infinity of absolute values of k plus 1 over a sub k. Right. Right, a sub k plus 1, put k plus 1 in here, negative 1, k plus 1, x minus 2, k plus 1. I don't know why I write 4 factorial like that. It's supposed to be 4 to the k. And we write a sub k will be that. Right, multiply reciprocal. Right, let's try to put a little smaller. Right, reciprocal 4 to the k on the top, negative 1 to the k, x minus 2 to the k. Yeah, this is a long problem, so I try to save some space. Right, Now we write this negative 1 to the k plus 1, and write negative 1 to the k, and then negative 1 to the first. Same thing for x minus 2 to the k, x minus 2 to the first. 4 to k plus 1, 4 to the k, and 4 to the first. 4 to the k on top, negative 1 to the k, x minus 2 to the k power. Right. There's a lot to simplify. 4 to the k, x minus 2 to the k power. What else? Oh, negative 1 to the k. Right, so that's what left. Negative 1, x minus 2 over 4. Now, we still have absolute values, right? The 4 at the bottom is positive, so we only need the absolute values on the top. Right? And absolute values are positive or negative, it doesn't matter. So I'm going to drop this negative sign because of the absolute values. Just need to write like this. Now, if we want this to be convergent, less than 1 for the series to be convergent, for the series to converge. Right. The nice thing about this is we have the limit for k goes to infinity, and we don't even have k, so we don't even need to write the limit because there's no k in here. So we have x minus 2 absolute values over 4 less than 1. Multiply 4 on both sides. We have x minus 2 less than 4. Right, so this, the 4 here is the interval convergence, and the 2 is the center. So this is the radius of convergence. Right, where's my ruler? Wait, so I'm going to write a number line. So we have the center convergent is the center is at 2. And the radius of convergence is 4, meaning that we go to 4 to the left and 4 to the right. So plus 4, 2 plus 4 is going to be 6. And 2 minus 4 is going to be negative 2. Yeah, because the radius of convergence is 4. So this distance have to be 4, and that distance is 4. Right. So negative 2 and 6. So first of all, we know the radius of convergence is 4. for interval convergence, if we write like that, it's going to be between -2 and 6. We don't know what happened at -2 and 6. So in that case, we have to check for the boundary, check for -2 and check for 6. So if we want to find the interval convergence, we need to check those 2 points. Right, we check the boundary first. For x equal to -2. Now x equal to -2, put -2 back into the series. So the series put -2 in it. And -2 to the k and this is k equal to 0 to infinity. Now -2 is -4. Now both of them, actually all of them, in the power of k, so we bring everything inside the power of k. We have -1 on the top, and then -4, and then 4 at the bottom, all of which to the power of k. Simple enough, right? So we can test the power of k, pour it out, on out. That's what we have. Now -1 and -4, that's 4 divided by 4, cancel out. So we just have 1 to the k. So I have 1 to the k power, or just 1, right? 1 raised to any powers. Now see what happened when 1 raised to infinity isn't that indeterminate. Yes, 1 to infinity is indeterminate, but we're not talking about that here, because each time k equal to 0, just 1, 1, 1, and 1. And so just 1. So we just have 1, plus 1, plus 1, plus 1. Because if we just do that indefinitely, this one is divergent, right? Because the n term does not go to 0, it cannot be convergent. So they just keep going, just getting bigger and bigger and bigger. If essentially it is equal to infinity, right? Because k go to infinity. So that's why this is divergent. So we know at -2 it will not work, so we're going to have the parentheses as -2. What happened at 6? We do the same thing. Put put 6 in for x. Right, put 6 in for x. Six minus 2 is 4. This one I just cancel out. And we just have so what does that mean? Now if we write this series out, -1 to the k power. By the way, that does not go to 0 either. So by divergent test, if the k term does not go to 0, as k go to infinity, this one is divergent. But we can just reason. Negative 1 to the 0 power is 1. Negative 1 to the first power is negative 1. So we just have 1 minus 1 plus 1 minus 1 plus 1 minus 1. Just keep alternating like that. There will not be a number at the end because it just keep changing from plus 1, negative 1. So as mentioned before, if the k term, if this term does not go to 0, as k go to infinity, the series is divergent. Right. Now we go back to the number line. This time we have from negative 2 to 6, and we know that it is divergent on both negative 2 and 6. So the interval convergence is not including the 2 and the 6, but it is between 2 and 6. So we write interval of convergence. From negative 2 to 6, not including the endpoint. Right. So when the problem for interval convergence, when we find the radius convergent, if it is a finite number, we have to check the boundary. Sometimes both of them will work, sometimes none of them will work in this case. So negative 2 and 6. Right. Let's look at another example. Of course, we can also write x between 6 and negative 2. Either way, can be in this form or that form. Right, let's look at another example. By the way, let me zoom out. Never mind, just we find the radius of convergence and then we check the endpoint. Right. I have another example here. We do the same thing, ratio test, and after that, if the radius of convergence is a finite number, check the endpoints. Right. So, ratio test. So first, this case we don't have k, we have n. That's okay. So let a sub n be x minus 5 to the n power over 1 plus 2n. Right, the ratio test. First, let R be the ratio as the index, in this case n go to infinity, of the next term over this term. Right. First we have n plus 1 here and here. Right, so it will be like that. We will put in n plus 1, and then for n plus 1, but just over a of n will be the same thing. Divide fraction is multiply reciprocal. I forgot to the n power. And this one, that will be 2n plus 2. 2 and 1 is 3, so we can write 2n plus 3. Right? 2n plus 2, 2 and 1 is 3. Multiply reciprocal. Right. Now the only thing we can rewrite is this to the n plus 1 power. Which will be x minus 5 to the n and x minus 5 to the first, and then O to n plus 3 and x minus 5 to the n. That cancel out. Now I'm going to write all of the 1 plus 2n and 2n plus 3 all over x minus 5. Right. I'm going to put 1 plus 2n on the top, 2n plus 3 at the bottom, and then x minus 5 I can just write by itself like this. Limit for n goes to infinity. Now notice that n go from 0 to infinity, therefore all of those are positive, so we don't even need absolute values for that, only need absolute value of x minus 5. Furthermore, x minus 5 does not have n in it, this limit for n, so we can say this x minus 5 is the constant. I should not say constant. X minus 5 is independent for this n, right? It doesn't have n in it, so we can just take it outside of the limit because it doesn't have n in it. We could do that for the previous example as well. Right. Now, this limit is easy, right? Highest power on the top, highest power on the bottom, cancel out 2n over 2n, so pretty much. As n go to infinity, the 2n is a lot bigger than 1 or 3. Cancel the 2n, we just have 1. That cancel out. So limit of 1 is just 1. There's no n in here, so that's just 1. So we have x minus 5 in absolute values. And the ratio test say that if we want this to be convergent, the ratio test have to be less than 1 for the series to converge. Right, so pretty much we have x minus 5 less than 1. Now of course when we write x minus 5 less than 1, absolute value of x minus 5 less than 1, the 5 is the center, the 1 is the radius of convergence. So this is the center, and that is the radius of convergence. Right. Now let's draw a number line. we have the center at 5. The radius of convergence is 1. Actually, let's just write it down. Radius of convergence. So from the center of 5, we go 1 up, 1 down. So add 1 going to give us 6, and minus 1 give us 4. Right. Now, if we want to check for the interval convergence, we need to check for boundaries, namely at 4 and 6. The radius convergence though is 1. Now check for boundary. Now at x equal to 4, I'm going to put 4 in for x. Uh, 4 minus 5 is -1. This is the alternating series because of that. So we actually can write this as -1 to the n, and then 1 over 1 plus 2n. Right, so now this is alternating series, so we use alternating series test. This is a sub n. So alternating series test. Where we let this be a sub n. And alternating series test, we test two things. What happened where the limit of that when n goes to infinity. This is easy. We take the limit of a sub n. And as n go to infinity, finite over infinity, so this equal to 0 because we have finite over infinity. So yes, that check. And the next is the series non-increasing. I just need to look for something real quick. We know that is decreasing for sure, but is a sub n non-increasing. This is simple. We can take derivative of this, but we just say as n increases, 1 plus 2n also increases. So if the bottom is increasing, the whole ratio will be decreasing. And it is decreasing, which means certainly non-increasing, so that check. So because of that, it is convergent at x equal to 4. So we say convergent at x equal to 4. Now we'll check for x equal to 6. Then I have space here, but right. Now put 6 in for x. So we just have one over 1 plus 2n. Right. I'm running out of space here. But if we do the limit comparison test or just direct comparison test or comparison test for this one, if we compare to ignore the one at the bottom, we compare to that. This is a harmonic series or the p series when p equal to 1. So this is divergent. So I've run out of space, so I just said by comparison test, I just said limit comparison test. To the series of 1 over 2n. This series is divergent. P series and p equal to 1. So this one is divergent. So it is divergent at x equal to 6. Yeah. You need to write more details than that on homework, but it is divergent. Right. Now, so it works at 4, convergent at 4, but divergent at 6. So in this case, we say interval convergent. It go from negative and go to 4 to 6, but including the 4, but not the 6. Yeah, so that's why we need to check the boundary. Sometimes one boundary will work, sometimes both of them will work. The previous example we have none of boundary works. So that's why we need to check. So ratio test will give us the radius of convergence. And then we're going to check the boundary. By the way, we only do that if the radius is a finite number. If this is equal to 0 or infinity, we don't need to do this. Only need to check the boundary when the radius of convergence is a positive finite number. Right, so we get to check boundary. Now, one more example for this, still ratio test. So I'm going to write h of k is that k factorial x to the k. and the ratio test are equal to limit k go to infinity a sub k plus 1 over a sub k. Right, a sub k plus 1, we're going to put k plus 1 here. Yeah. And a sub k. So this one we don't have a quotient, so just k. So no need to k plus 1. No need for multiply reciprocal. Right, k plus 1 factorial is k plus 1 times k factorial. X of k plus 1 is x to the k, x to the first. When we multiply them, combine the exponents over k factorial x to the k. X to the k cancel out, k factorial cancel out. End up with that k plus 1 times x. Of course, we only need the absolute value for x. Now, this has to be less than 1 for it to be convergent. Alright, so, but I don't know why I write x here. That should be k, right? Now, as k go to infinity, k plus 1 go to infinity. So if this is anything else, any constant times infinity, it will be infinity. Unless, of course, x has to be equal to 0. If x equal to 0, then we have the limit of 0 as k go to infinity. So we say this one equal to 0 if absolute value of x equal to 0. So notice that when we have absolute value of x equal to 0, we're going to do that first, and we have the limit of 0. I should have write that out. Right. Now if we have absolute value of x equal to 0, we have the limit as k go to 0, k go to infinity of 0, and this is equal to, if it is equal to something else, we can factor it out. If it is not equal to 0, we can pull it out. But this one equal to infinity. So something else times something other than 0 times infinity. So it's infinity. So if we want this to be convergent, we're going to need this for the series to be convergent. So we have absolute of x equal to 0. So in this case, that is the radius convergent, 0. Center, of course, at 0. This will be divergent. Because we have infinity, which is not less than 1. This is equal to 0. Yeah, So if it is equal to 0, then it is less than 1, which is good. So this is convergence. For absolute value x equal to 0. So the radius of convergence that number are equal to 0, and the interval convergence we have the center at absolute value of x equal to 0, so interval convergence actually is just an isolated point, 0. Right? If absolute value equal to 0, then the number must be 0. Right, so that is the radius of convergence, interval convergence. I have quite a few examples of those. Right, next, working with power series. Now, what can we do in power series? Actually, we're going to do this more in the next section, but for now, what we can do is, suppose it is convergent absolutely, then we can add, we can subtract, just combine function pretty much. We can add or subtract the power series, we can multiply, and we can, as long as it's independent of k, we can multiply that, the power series, and do this. Like I said, add or subtract, we will do that in the next part of the section. Right now we just do the very fundamental thing though. Right. Now let's do some example. Find the power series of the following function. Right, what can we do here? This go back to the first part of the section. By the geometric series, we're going to have that, but only for x between -1 and 1. So I will write, if we have 1 plus x squared, or we can put this as a power series and that equal to 1 over 1 minus x if absolute value of x less than 1. Right. So this is from the geometric series. So if we can write in this form, we can write as the power series. So we're going to find a power series for this. Right, first, it's very easy. I'm going to bring out the x to the 5th, and then I have 1 over 1 minus x. Now using this theorem, we write off that by either a series, or we can put this in the summation form. So we'll write that as 1 plus x squared. Or if we want to, we can also write this as x to the 5th in the power series. X to the k. So either we write out the terms or we use the summation. And then we just multiply it out. So x to the 5th, x to the 6th, x to the 7th, and so on. Or here we can, that one independent of k, we can take it inside. Multiply two things with the same basis. So we will combine the exponent. So either we're going to write like this, or we're going to write in the summation form like that. Either way, simple enough. But we have to utilize the fact of the part of the geometric series 1 over 1 minus x is equal to that. So it have to be the form of 1 minus something. Right. Next we have this example. By the way, this one is too easy, so make it a little more complicated. Why don't we change this into 4? I will change the note online so you don't have to worry about this. So let's change it to 4. A little more interesting, right? Because after all, we need to have 1 over 1 minus something. So the one there is good. Not going to touch that. But what we need is the bottom is 1 minus something. So in order to do that, we have to divide by 4 top and bottom. And then when we multiply across, we have 1/4 on top. And 1/4 times 4 is 1. And 1/4 times 2 is negative x over 2, or we say it 1/2 x. Right. Then we can bring out the 1/4 in front. So we need the 1 on top, and we need 1 minus something at the bottom. We can write 1/2 x or x over 2, either way. I'm just going to keep 1/2 x like that. Right? By the way, just to make sure the answer is correct, on this one, when we write the answer, make sure that we write whatever. Yeah, just write that condition there. Just make sure f of x is less than 1, so the geometric series will work like that. Right, so multiply 1/4 top and bottom. 1/4 factored out, and then we have 1 on top. At the bottom, 1 minus 1/2 x. So now we can write this as a power series. One plus 1/2 x plus 1/2 x squared 1/2 x cubed or if you want to write that in the summation form, is equal to 1/4 summation k equal to 0 to infinity 1/2 x to the k power. Right, and then we can just multiply this out. The rest is just simplification, simplify them. So 1/4, and this is 1/2 x, so 1 over 8x. 1/2 square will be 1/4, from 1/4 is 1 over 16 x squared. 1/2 cube is 1 over 8, 1 over 32 x cubed, and so on. Or we can write this in the summation. And so 1/2 to the k power and x to the k power, so we have 1/4. And 1/2 to the k power we can write as 1 over 2 to the k power x to the k power, and then multiply the 1/4 inside if we want to. By the way, the 1 over 4 is that 1 over 2 square, right? Now the 1/4, 1 over 2 square. So we can combine those two. The series will be as 1 over 2 to the k plus 2 x to the k. Yeah, so we can write like that, or like that. Right, regardless, we still need to have 1/2 x less than 1 for the series to be convergent, so we can write like that. Right, 1/2, of course, we can multiply by 2 on both sides, so that part is not really important. Right, notice that the only thing we can combine series now is using the geometric series. So the geometric series, we need to write this as 1 over 1 minus negative x squared. So always have to be 1 minus something. And in that, we can write as the geometric series. There's no coefficient in front, so just 1. The whole thing here. Like that. Or in the summation. Negative x squared to the k power. So we'll have 1 minus x squared plus x to the 4th minus x to the 6th, and so on. Or the summation. We can write negative 1 to the k x squared to the k. Power to another power, we can combine them. So this is an alternating series. But of course it only works if we have negative x squared less than 1. Absolute values are positive or negative. It's the same thing. And absolute value of x squared less than 1, meaning that we can take square root on both sides. So, or we can just say x, absolute value of x less than 1. Right, and only works if x is less than 1. If x is bigger than 1, we cannot write as a power series like this. Right, so we can certainly multiply and divide power series. Like I said, in the next section we do a lot more of this. But for now, let's do a few things. We will do more in section 11.4 also. But what we can do here is if the function is defined on the interval, if this is defined, then the function is continuous. And not only that, we can take the derivative and the integral of the function, or the derivative or integral of term by terms. So how do we do this? So we can take derivative term by term or integral term by term. So we have two examples here. One of them differentiate. So we're going to take derivative term by term. So we can look at this. We can take derivative in the series form, or we take derivative of that form in summation form or not. So we're going to do both. First, we differentiate the summation. Now this will be easy if we have k equal to 0 to infinity, x to the k. Where we take derivative, we're going to bring down the k and the original power minus 1. Right? Simple enough. Power rule. Now, just little things here. When k equal to 0, if you put 0 in here, what do we have? Right. If we put in 0 in here, we're going to have 0 x to the 0 minus 1, right? And then we can continue the series starting from 1. So that case we just split out one term when k equal to 0, and then after that the series will continue from 1 up. So why do we write like that though? Because 0 times anything is 0. So this is the answer. So in the summation form, the series will start from 1. Right. So if that is differentiate in the summation form, now we can differentiate term by term. Right, so we have the series or the function is 1 plus x squared plus x cubed and so on. When we take derivative of 1 is 0, derivative of x is 1, derivative of x squared 2x, x cubed 3x squared, and then the next one will be 4x cubed and so on. So we can write like that. So whether we want to write term by term or we want to write summation, either way it works. Right? Now, of course that is differentiate. Now, but what if we take derivative of f of x? Now back to the function. By the way, that is how we differentiate a series. Now back to a function. We have f of x equal to 1 over 1 minus x, or we can say 1 minus x to negative 1. I will take derivative. That will be negative 1 minus x to minus 2, and then the chain rule says derivative of the inside, which is negative 1. Clean that up. Derivative is equal to negative, so 1 minus x squared, x to negative 2, or 1 over 1 minus x squared. So if we take derivative term by terms, if we take the derivative of the summation form, and if we take derivative of the function, all of them are derivative, so we can make all of them equal. So after all of this, we can have the power series for 1 minus x squared is 1 plus 2x plus 3x squared for x cubed, or in summation form k xk minus 1. Right. So all of them are equivalent because it's just derivative, right, in just different forms. So now after this, we write the power series for that, which is kind of nice. Now next, so we certainly can take derivative term by terms. How can we integrate term by term? So first we're gonna use this equal to tangent inverse of that. Now write the power series for tangent inverse. Let's see. Right, first we did that earlier, right? 1 over 1 plus x squared in this form or in this form. Of course, as long as absolute value of x less than 1. Right, so try to write small here. So from the previous example, this is what we have. 1 over 1 plus x squared. If we're going to write by terms, or in the summation form, by the way, now I just realized that in the previous example I forgot the k there. Right, now we just integrate term by terms, or we can integrate the whole summation form. Now actually I can write like this term by term, or I just gonna integrate all of them. Now I'm just going to integrate the whole series here. So this is integrate term by term, and this I will integrate I can put the integral in front, or I'm just going to put the integral. Right, so integrate term by term or in the summation. I'm going to keep that for now. Integral of this is x minus x cubed over 3 minus x fifth plus x fifth to the 5 minus x to the 7 over 7 plus the constant c. Now get back to that constant c business in the little bit, but for now integral of that series still summation -1 to the k power. This one independent of x, so just going to take that outside of the integral. Integral of x to the 2k will be x to the 2k plus 1 x over 2k plus 1. That's just simple power rule. Plus the constant c. We still need to have the constant c. Now, of course, if we integrate, that one is given equal to tangent inverse x plus c. right? By the way, notice that we can just write one constant c on one side, right? When we integrate both sides, we only need the constant c on one side. So I choose to keep this constant c, and those two are equivalent, so we don't have. Only need the constant c on one side. This is dot 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 because they just keep on. Now let's just solve for some values for it. Now at x equal to 0, this is the initial value problem, so we solve for that. At x equal to 0, if x equal to 0, we start with tangent inverse of 0 plus c equal to all of x equal to 0, right? 0 cube over 3, 0 to the 5th over 5, 0 to the 7 over 7. In the series, zero to the 2k plus 1 over 2k plus 1. Yeah, we only need a constant on one side, on this side. Now, tangent of 0, tangent inverse of 0 is 0. We have a calculator here, why don't we use it? So that's 0. So we have 0 plus c, and all of that equal to 0, all of that equal to 0. So from here, of course, c has to be equal to 0. So because of when we write a series like that, c has to be 0. So with that, we can say tangent inverse of x plus c, but c is 0. So we just say tangent inverse is equal to x minus x cubed over 3, x fifth over 5, x7 over 7, and so on. Or we can write as the series, as a summation. Right? So, of course, that's just that. Now, so that's when we integrate term by terms, or we integrate the summation. Notice in integral there's a constant. So we can put the constant either in one of the three. I choose to put the constant here on this side. Initial value problem, we can solve for that. Now, what I want to extend this problem is that now tangent inverse is equal to this series, right? Now, what happens if we let x equal to 1? By the way, what is the tangent inverse of 1? Great, what's that? Right, if we keep this in degree mode, it's 45 degrees. So if we have x equal to 1, let's put 1 in for x. So 1 minus 1 cubed over 3. So just, if we put 1 in for x, doesn't matter what the power is, it's still 1, right? Or in the power series, or in the summation form, -1 to the k. The x here equal to 1, so we just have 1 over 2k plus 1. So what the big deal of this? Now, big deal of this is tangent inverse of 1 is pi over 4. right? Then what really a big deal of this is if we multiply 4 on both sides. So we have the definition for pi. So that means if we want to estimate pi, we can write like that. I forgot the 4, but I'll do that later. Of course, you multiply the 4 in the series, multiply 4 in here, so we can write the 4 on top like that. Right, so let's see what that really happened. Math number summation. Right, let's go x equal to 1, 0. Let's do 1,000 terms, not 10,000, right? The series -1 to the, I use x instead of k, and then the fraction. Don't really want to do that. The top we have x to the 2k plus 1, but x equal to 1. 1 raised to any power is still 1. And then, right, let it run. Right, it will be a while. Anyway, so that is, on that side, is an approximation for pi. So how good is this approximation? Now, if you go back to the alternating series, that is section 10.6, it says that the remainder of the power series using the alternating series, the remainder of alternating series is going to be less than the next neglect term. So if we have 1,000 terms, what is the 100, 1,001, the 1,001st term, whatever that is? I forgot to multiply by 4, sorry. So that is pi. So that means whatever, this is not a very good approximation for pi, because this one, the rate that go to pi is extremely slow. Because if we need 1,000 terms, if we use 1,000 terms like we did over there, the remainder is actually less than the 1,001st term. Meaning that what is the actual error of this is where we put 1,001st here. So we'll have 4 over 2 times 1,001. So the error is going to be less than that. So the actual values of pi, and that is going to be less than the n plus first term. So if we take the actual values for pi minus this, so it is off by that much, of course. The remainder is going to be less than that. So not a very good approximation, but still a very nice problem. So later on, if we want to estimate pi, we can just do this. Even though there's a lot different way to estimate value for pi, this is probably not the best way to do that, but still very nice, simple enough. 4 times 1 minus 1/3 plus 1/5 minus 1/7. So the series is simple enough, a good approximation. Probably not very good, but the point for approximation usually using power series is that whether it's good or bad approximation, I say this is not a very good one, because we need a lot of terms for the approximation to be very good. So, but the point here for power series is if we can go on as far as we want to, the accuracy will be as good as we want to. So that's the idea. We can get the approximation to be as good as we want to if we have enough terms. So that's the spirit of using the power series to approximate something. But other than that, I will stop section 11.2 here. We do a lot more example in combining power series in the next two sections. But that's it for this section. Thank you for watching.